All right, please, let's look up. We are looking at enzyme inhibition. Please look up because so many things I will say now, I did not give you in that note. So please listen up. Now, when we talk about enzyme inhibition, recall that an enzyme catalyzes biochemical reaction, right? Is it not? Now, where you place the substrate for that enzyme to catalyze is called the what? Active site of the enzyme, right? So let's assume this is the active site. An enzyme can have other sites other than the active site. If it has another binding site, let's say this, other than the active site, this additional binding site other than the active site is called the what? This is called the allosteric site. Thank you. So this is the allosteric site and this is the active site. But if the substrate wants to bind, where will it bind? Is it in the active side or allosteric side? Active side, right? Good. Now, we have molecules we call inhibitors. Personally, I call them enemies of progress. Now, inhibitors, what they do is, they know that enzymes catalyze, speed up chemical reaction, right? Inhibitors will go and bind with the enzyme, and as they bind with the enzyme, they will either reduce the activity of that enzyme, the rate at which it is catalyzing the reaction, or they block the activity completely. Those are inhibitors. And that process whereby the inhibitor binds with the enzyme and either reduces the activity or blocks it completely is called what? Enzyme inhibition. Now, we have two types of enzyme inhibition. We have the irreversible inhibition and the what? Reversible inhibition. When we say something is irreversible, what does it mean? You cannot go back, right? Now, in irreversible inhibition, irreversible inhibitors bind to this enzyme with a covalent bond. Very strong bond. So as they hold the enzyme tight, you're not going anywhere. Remember, inhibitors, they are either reducing the activity or blocking the activity completely, right? Irreversible inhibitors, they say I have nowhere to go. They'll just hug the enzyme and remain like that with a strong bond. So nothing you do, simple dialysis, cannot remove the inhibitor from the enzyme. So we say that type of inhibition is what? Irreversible. Because the inhibitor is binding to the enzyme with a very strong covalent bond. But the second type of inhibition, which is reversible inhibition, that one, they are enemies of progress that are learning work. They will bind to the enzyme, but not with a very strong force. So they just bind with a non-covalent force, hold the enzyme weakly. So simple dialysis can remove the enzyme from the inhibitor from the enzyme, right? And so the enzyme activity can be restored. But recall that in irreversible inhibition, can the activity of the enzyme be restored? No, right? But in reversible, the activity of the enzyme can be restored. Good. Now we have classes or types of reversible inhibition. And please, I would like you to pay great attention here, because you don't have to cram anything. The first kind of reversible inhibition we have here is competitive inhibition. Competitive inhibition. Now, look at this again. Let's assume that this is the active site. And let's assume that this is the allosteric site also. And we all know that where the enzyme will bind, where the substrate will bind to the enzyme for catalysis to take place is what? Active site. Now, competitive inhibitors, they will now watch and say, okay, substrates will bind to this active site for catalysis to take place. They will not tell themselves, okay, so if I block this active site, it means substrate cannot bind, eh? Said yes. But there is a rule. Anything that can bind to this active site of the enzyme must have the same shape as this active site, true or false? right? So, in fact, the lock and key model, no substrate can bind here for catalysis to take place except it has the same shape as this active site. Is it not? Now, if the inhibitor studies that, knows all these theories, we will now say the competitive inhibitors have the same shape as the substrate. So if the shape is like this, if the substrate looks like this, so it can fit here, the inhibitor also looks like this, so has the same shape as the substrate. So you see that since they have the same shape, any of them can bind here, right? So competitive inhibitors, they have the same shape as the substrate, so any of them can bind to the active site. If the inhibitor binds first, what do you think will happen? The enzyme activity is blocked, right? But remember, it is under reversible inhibition, meaning it can also fall out. Now let me ask you a question. If the inhibitor binds first and you want the inhibitor to fall out, what do? Thank you very much. You increase the concentration of the what? Of the substrate. Because the one that has the highest concentration will be the one to bind. Do you understand? So if we want to represent this, you can say this is the enzyme, right? Normally, enzyme plus substrate is supposed to give us what? Enzyme substrate complex. Then if catalysis take place, we have what? Product. But remember that enzyme is not used up in a reaction, right? So we're having enzyme plus product. Good. But remember that can a competitive inhibitor bind to the enzyme, bind to the active site? So competitive inhibitor can also bind here to the enzyme. So if the competitive inhibitor binds, what do you think will happen? Product will be formed, right? If inhibitor binds to the enzyme, what do we have? Inhibitor enzyme complex, right? And this is a dead end, because catalysis cannot take place here. Is it not? But if the substrate binds, catalysis takes place to form products. If inhibitor binds, we have a dead end. So this is competitive inhibition. Do we understand? So the bottom line here is, in competitive inhibition, the substrate and the inhibitor, they have what? The same shape. So they are competing to bind to the active site. Do we understand that? All right. Now, the second form of inhibition, the second form of reversible inhibition is a non-competitive inhibition. Non-competitive. Let's come back to this diagram here. In competitive, why was the inhibitor able to bind to the active site? It has the same shape as the substrate, right? But non-competitive inhibitors, they don't have the same shape as the substrate. So since they don't have the same shape, can they bind to the active site? They cannot bind to the active site, right? So they will now look and say, but I really want to hinder this enzyme from making it in life. What will I do? I don't have what it takes to come directly to this place. So what do I do? And now remember that as he's thinking, non-competitive inhibitors, now remember that there is another binding site called the what? So we are in non-competitive, right? So the non-competitive inhibitor will now think and say, okay, since I cannot bind to the active site because I don't have the same shape as the substrate, there is another site I can bind. Do you get? So the non-competitive inhibitor will now bind to the other side called the what? Allosteric site. So it will bind here, and as it binds here, it will now change the shape of this active site so that even the substrate can no longer bind. They are very wicked. You see, non-competitive inhibitors be like, since I cannot bind, nobody will bind. And since I cannot prevent it directly, since I cannot prevent it directly, I'll pass through the frame. It's just like competitive inhibitors. Competitive inhibitors work in admission office. So as they are in admission office, as they see your name, they will not even allow you to enter the university, they remove your name because they are working in the admission office. But now non-competitive inhibitors, they are not working in the admission office, and at the same time they don't want you to get admission. So they now remember they have a friend they can pass through. That friend now will now spoil everything. All right, so the bottom line here is competitive inhibitors, they have what? The same shape as the what? But non-competitive inhibitors, they don't have the same shape, right? So where do they bind? The allosteric side. Now look at this. If we have an enzyme plus substrate, we have what? Enzyme substrate complex, right? And if catalysis takes place, we have enzyme plus what? Now, can the inhibitor bind here? If the inhibitor binds, what do we have? Enzyme inhibitor complex, right? At this point, can substrate bind? Can substrate still bind? Can substrate bind? Now look at this. If we have enzyme substrate complex, can inhibitor still bind? Inhibitor can still bind because the inhibitor is not binding at the active site, it's binding at the allosteric site. So if it binds here and the substrate was there to fall out, so just give this one carry over until it gives extra here, until you be tired, you go home. So basically, competitive inhibition, the inhibitor can bind to the free enzyme, and the inhibitor can also bind to the enzyme substrate complex. Do we understand that? I'll take that again. In competitive inhibition, the inhibitor can only bind to the enzyme, right? Because it's binding at the active site. One must bind. It's either the inhibitor is in the active site or the substrate is in the active site. So inhibitor cannot bind to the enzyme substrate complex in competitive. But in non-competitive, the inhibitor is binding as well. The allosteric site. So if the enzyme is free, the allosteric site is still free. Inhibitor can bind. If the substrate is already here to form the enzyme substrate complex, this place is still free. Inhibitor can still bind and change the shape. Substrate falls out. Now let me ask, increasing the substrate concentration in non-competitive inhibition, can it remove the inhibitor? Listen carefully. Increasing the substrate concentration in non-competitive inhibition, can it fall out the inhibitor? No, they are not binding in the same place. So if you are increasing the substrate concentration, substrate will just be moving around this place. Substrate will not be coming here. And the inhibitor is doing it from the backyard. You just know say something they do you, but you don't know who they do you. That is how they are. They are very wicked. But the most wicked set of inhibitors, enemies of progress, is the uncompetitive. I don't even like teaching this uncompetitive because they are very wicked. Now, let me explain the uncompetitive. In uncompetitive inhibition, the inhibitor does not have the same shape as the substrate also. But the problem with uncompetitive inhibition is uncompetitive inhibitors will allow you to succeed first. Will allow you to get into the university first before you start acting. So uncompetitive inhibitors can only bind to enzyme substrate complex. They cannot bind to free enzyme. Are we following? Are we following? Yes. Competitive inhibition. In competitive inhibition, competitive inhibitors can bind to free enzyme. They can bind to enzyme substrate complex, right? But uncompetitive inhibitors can only bind to enzyme substrate complex. So if we have something like this, enzyme plus substrate to give enzyme substrate complex, and catalysis takes place to give us enzyme plus product. Can an uncompetitive inhibitor bind here? Can an uncompetitive inhibitor bind here? No. We said uncompetitive inhibitors cannot bind to free enzyme. They can only bind to what? enzyme substrate complex. Then when they bind to the enzyme substrate complex, they will now form enzyme substrate inhibitor complex, and they will now inhibit that reaction. So basically what I've said so far, competitive inhibitors, they have the same shape as the substrate, so they compete for the active site, right? Non-competitive inhibitors, they don't have the same shape, they bind at the allosteric site, and we say they can bind to the free enzyme or the enzyme substrate complex. While uncompetitive inhibitors, they don't have the same shape and they cannot bind to free enzymes. They only bind to what? Enzyme substrate complex. I'll give you the shape of the graph and we call it a day on this topic. So you can sketch. Alright, now let's look up. We've seen the three types of reversible inhibition as competitive, non-competitive, and uncompetitive. Alright, now how can we represent them graphically? Now their graphical representation can be seen on the board here. If you plot your graph and your graph looks like this, that is, this plus I, this is the line when inhibitor is present, and this is when inhibitor is absent. The graph, you're always plotting 1 over V against 1 over substrate concentration. This one is when inhibitor is present, and here is when inhibitor is absent. Now if you are plotting your graph and the two lines intersect on the y-axis here, the two lines intersect here, you say that type of inhibition is what? Competitive. Because in the graph they will not tell you the mode of inhibition. It is after plotting you should be able to tell them this is competitive, this is non-competitive, this is uncompetitive. So yeah, if you plot and the two lines intersect on this y-axis, you call it what? Competitive. Now if you are plotting and the two lines intersect on the x-axis, look at it, you say it is what? Non-competitive. Then if the two lines are parallel to each other, you call it what? Uncompetitive. Are parallel to each other, uncompetitive. Now let me explain this issue. You agree with me that in competitive inhibition, the inhibitor and the substrate, they have the same shape, right? And so both of them can bind, right, at the active site. If you look at this, we have just one velocity here, 1 over Vmax. Is it not? We have just 1 over Vmax. We are not having Vmax for when inhibitor is present and when it is absent. No, we don't have that. We have for only one of them. You see why? Yeah, we have Vmax for when inhibitor is present and when inhibitor is absent. Do you know why now? Let me start from here. Just hold on. Now, if you look at this, in non-competitive inhibition, I will allow you to write. Listen up. Yeah, we see that we are having 2 1 over Vmax, 1 over Vmax, right? Yes. Good. This is the reason why. In non-competitive inhibition, we agree that this is the enzyme, and non-competitive inhibitors, they don't have the same shape as the active as the substrate, right? So they can only bind to the allosteric site, is it not? But now we agree that non-competitive inhibitors can bind to free enzyme and can also bind to what? Enzyme substrate complex, right? Good. Now if the reaction is proceeding without inhibitor, this is the velocity or the maximum velocity. But if inhibitor is added, maybe the inhibitor binds to the enzyme substrate complex, the rate of the reaction, will it reduce or increase? Will the rate of the reaction increase or reduce? If the inhibitor is added, will the rate of the reaction increase or reduce? Reduce now, right? That is why we have another velocity here for when inhibitor is added and when inhibitor is absent. But the Km remains the same. The bottom line here is this. Please, anyone you see prime is for when inhibitor is present. Now, in competitive inhibition, Vmax remains the same, right? But we have different Michaelis-Menten constants. In non-competitive, we see that Km remains the same, but Vmax differs, right? In uncompetitive, the one I hate the most, the two are different. We have different Vmax and different Km. Now, for now, we'll leave it as it is. Now, if you look at this, I'm saying Km prime. Prime. This Km prime, the difference between Km and Km prime is this. Km prime, I said prime is used when inhibitor is added, right? So Km prime is same thing as Km times a factor called the inhibitor factor. The inhibitor factor is always 1 plus inhibitor concentration all over Ki. So Km prime, which is called the apparent Km, is equal to Km times this factor. This factor here, 1 plus inhibitor concentration all over Ki, is called the inhibitor factor. V max prime, apparent Vmax, is the same thing. You multiply Vmax by this factor. So apparent Vmax is still Km times this factor. So if you don't write prime, you can put this full stop there in place of prime. All right, so take note of this relationship.